Hello.
Hello student, today we are starting wave optics. When light will behave as a wave, that is the first concern, okay? When wavelength of light remains of the order of size of obstacle or aperture, then light behaves as a wave and we study wave optics. In the phenomenon of wave optics, we study interference of light, diffraction of light and polarization of light, okay? Interference, diffraction and polarization. They verify the wave nature of light. These are the phenomenon to verify the wave nature of light. Today we will study interference of light. Okay. So dear student, when light will behave as a wave, light will behave as a wave when wavelength of light, if lambda equal to wavelength of light and a equal to size of obstacle or aperture, when lambda is of the order of a, then light behaves as a wave. And we study three phenomena. We study interference, diffraction, and polarization. Okay. So, dear student, let's start with the interference of light. As the name indicate, interference means two or more than two light wave will come and interfere or superpose. Okay, then interference will take place. So, what happens when light interfere? In case of interference of light, somewhere we get more brightness, means more intensity, means constructive interference, okay? Means same phase superposition. And what happens when destructive interference takes place? At some point in the medium, we get dark places or less light, okay? This is the case, okay? So, dear student, what is interference? It is a phenomenon in which when two light waves of nearly same amplitude and zero or constant phase difference between them. propagates in same direction. Propagates in same direction. Then resultant intensity at some point remains maximum and at some other point remains minimum. This phenomenon is called interference. Okay. So you can understand phenomenon in which intensity variation takes place. Okay, is called interference. Now let's understand about the coherent sources of light. Coherent sources are must for stable interference. What is coherent source? The sources of light from which emitted waves have same frequency and constant phase difference between them are called coherent sources of light. Okay. Emitted waves have same frequency and constant phase difference. Phase difference should be 0. These sources are essential for stable, that is sustained interference of light. They are obtained either by division of wavefront or division of amplitude technique. They are obtained either by division of wavefront or division of amplitude technique. Okay. The experiment in which coherent sources are obtained by division of wavefront are YDAC experiment, Fresnel biprism experiment, Lloyd mirror experiment, and the math experiment in which coherent sources are obtained by division of amplitude method are color in thin film experiment. Okay. Michelson interferometer, Newton's ring experiment. And what is non-coherent sources of light? Two independent light sources are non-coherent sources of light from where emitted waves we do not maintain phase difference between them. Okay, constant phase difference between them. Simply here intensity will be simply add up. In case of non-coherent sources, we do not get stable interference pattern. Okay, here intensity is direct addition, okay? I1 plus I2 plus I3, whatever it is, okay? This is the case of non-coherent sources of light. Now, dear student, what is condition for stable interference of light? Condition for stable interference of light. First of all, sources of light must be coherent. Sources of light must be coherent sources. Second, for best interference, amplitude should be same. Or nearly same. Light waves must propagate in the same direction. Light waves must propagate in same direction. Wavelength must be same. None of the waves should be polarized. If anyone is polarized, state of polarization must be same. State of polarization must be same. These are the important conditions for stable interference pattern, okay? And what happens in the interference? Energy remains conserved, only distribution of energy takes place, okay? Redistribution of energy takes place. Now let's see about the geometrical path difference. The path difference created due to geometrical path is geometrical path difference. Let us see here. Suppose this is source S1, this is source S2, and separation between these two sources is small d. And so distance between plane of the source with the screen, this is screen, is capital D. This is midpoint of the screen. Now let us assume this is a point P at the screen, and light waves are moving from here to here. So this is geometrical path length S1P and this is geometrical path length S2P. S2P minus S1P is called geometrical path difference. S2P minus S1P is called geometrical path difference, okay? In the question, it is given when D is quite less in comparison to D, you have to determine S2P minus S1P, that is geometrical path difference, okay? So it is very simple. Now we can see. Let us assume this distance is x. Since this is d by 2, so this is how much? This is x minus d by 2. And this is how much? This is x plus d by 2. let us say this point is A and this point is B. So in triangle S1AP and also in triangle S2BP, these are right angle triangle, we can write the equation, okay? In triangle S1AP, S1P square equal to D square plus X minus D by 2 whole square. So what is S1P? D square plus X minus D by 2 whole square. This whole power 1 by 2. And what is in triangle H2BP? What is H2P? In a very similar way, H2P is D square plus X plus D by 2 whole square. This whole power 1 by 2. Okay, now this is equation number 1 and this is equation number 2. If we make the difference of equation 2 and equation 1, we can easily get S2P minus S1P. Okay, now let's see what is S2P minus S1P. H2P minus S1P equal to D square X plus D by 2 का whole square power 1 by 2 minus D square plus X minus D by 2 whole power 1 by 2. Now we can write D square, this is 1 plus X plus D by 2 square upon D square whole power 1 by 2 minus D square 1 plus X minus D by 2 whole square upon D square, this whole power 1 by 2. Since in our case small d is very less than capital D, so we are applying binomial expansion relation. So this gives us D 1 plus X plus D by 2 whole square upon 2D square. Now minus D 1 plus X minus D by 2 whole square upon 2D. After solving this, we get this dd will get cancelled. X plus D by 2 whole square upon 2D minus X minus D by 2 whole square upon 2D. After solving this, we will get xd upon d. This is geometrical part difference, okay? So remember, this is xd upon d, okay? And by trigonometry method also we can easily get this formula. Let's see. This is S1 and this is S2. And this is small d. And this is capital D. This is midpoint. And this is a point P where light waves are reaching. So S2P minus S1P geometrical part difference. What we are doing? We have just dropped a perpendicular here. Since S1 and S2 are very close to each other, so S1, this point, D point, D point, S1D and S2D will also be very close to each other. So dear student, if this angle is theta, Then this is if this is 90 degree, we will consider this also to be 90. If this is theta, this is 90 minus theta, we will consider this to be theta. Okay, and this S2P minus S1P is S2N. This is geometrical part difference. In this triangle, we can, in triangle DMP, we can write tan theta equal to x upon capital D. And in this triangle S1, S2, N, we can write sin theta equal to S2N upon S1, S2. Since sin theta approximately equal to tan theta, so we can write S2N equal to what? XD upon D. Okay, this is what is the geometrical part difference. So remember, geometrical part difference is XD upon D. Okay. Now let's see mathematical interpretation of light, interference of light. Mathematical interpretation for interference of light. Mathematical interpretation for interference of two light waves Now, dear student, let's see mathematical interpretation for interference of two light waves. Okay. Let's see. We are writing their equation in the form of progressive wave. This y1 is displacement due to first wave, a1 is amplitude of the first wave, and this is sine omega t. And y2 equal to a2 sine omega t plus phi. Let us assume phi is initial phase difference which is constant with time, okay, which is not changing with time. Now from principle of superposition, we can write y equal to y1 plus y2. Since both the waves are moving in the same direction, so we can write y equal to y1 plus y2, okay. From the phasor method, we can directly add up, okay. y1 equal to a1 sin omega t and y2 equal to a2 sin omega t. Let's plot the phasor diagram like this. This is phasor for omega t, okay, having amplitude a1. In trigonometry, angles are measured in anti-clockwise direction. This is having amplitude a2. And this angle is phi, okay. Now what we have to do to find the resultant displacement and equation of the resultant wave? Make the vector component of a2, okay. When we will making vector component of a2, it will be a2 cos phi along a1 and a2 sin phi will be perpendicular to a1, okay. So dear student, let's make the component. This is a1 plus a2 cos phi and this is a2 sin phi. This is the resultant amplitude. Let us assume this angle is theta. Since a1 plus a2 cos phi and a2 sin phi are at 90 degree, okay. a1 plus a2 cos phi and a2 sin phi are at 90 degree, okay. So what will be the resultant? Resultant will be equal to a1 plus a2 cos phi whole square plus a2 sin phi whole square. When we solve this equation, we will get a1 square plus a2 square cos square phi plus 2 a1 a2 cos phi plus a2 square sin square phi, okay. a1 square plus a2 square cos square phi to a1 a2 cos phi plus a2 square sin square phi. Since cos square phi plus sin square phi equal to 1, so we can write the equation. We can write the equation of resultant amplitude. This is equal to under root a1 square plus a2 square plus 2a1 a2 cos phi. This is the equation of resultant amplitude. Okay. And since intensity is directly proportional to square of amplitude, okay, so we can write the equation of intensity also. I1 equal to I1 plus I2 plus 2 under root I1 I2 cos phi. Where I1 is A1 square unit, I2 equal to A2 square unit, okay. So dear student, and what about the equation of resultant wave? Equation of resultant wave will be equal to R sin omega t plus theta, where tan theta is A2 sin phi divided by A1 plus A2 cos phi. This is the equation of resultant wave, okay. You can see value of R and I depends on the initial phase difference, okay, phi. So there are two types of interference. First, you should know what is relation between phase difference, path difference, and time difference, okay. This is also very important thing. See here, if phi equal to phase difference delta equal to path difference and del equal to time difference, then this is the relation phi upon 2 pi equal to delta upon lambda equal to del upon t. This is the relation to convert phase difference, path difference, and time difference, okay. Now dear student, there are two types of interference. One is constructive interference, another one is destructive interference. Types of interference. There are two types of interference. One is constructive and another one is destructive. And another one is destructive interference. In case of constructive interference, when superposing waves meets in same phase, okay. Superposing waves meets in same phase. In case of destructive interface, superposing waves meets in opposite phase. Okay, now let's see. And the condition for constructive interface is phase difference is 2n pi, path difference is n lambda, and time difference is nt. And here condition is phase difference is 2n minus 1 pi, path difference is 2n minus 1 lambda by 2, and time difference is 2n minus 1 t by 2. Okay, these are the condition. Now let's start constructive interference. Constructive interference. Of light. Dear student, when superposing waves meets in same phase, okay, resultant intensity remains maximum. In this situation, phase difference remains equal to 2n pi. That is 0, 2 pi, 4 pi, 6 pi like this. Okay, so value of cos phi becomes equal to 1. In this case, R becomes equal to R maximum. This is equal to A1 plus A2. If A1 equal to A2 equal to A node, then R equal to R maximum equal to 2A node. And in a very similar way, intensity becomes I equal to I maximum, that is equal to I1 plus I2 plus 2 under root I1 I2. It is more than sum of individual wave intensity. Okay, if A1 equal to A2 equal to A node, then I1 equal to I2 equal to I node. Then this becomes equal to 4I node. Then this becomes equal to 4I node. Okay. So in case of constructive interface, intensity increases, brightness increases. Okay. Now let's see about the destructive interference. Destructive interference of light. In this case, phase difference remains equal to odd integer multiple of pi. That is, if n equal to 1, 2, 3, 4 like that, then phase difference become equal to pi, 3 pi, 5 pi like that, and cos phi becomes equal to minus 1. So value of R becomes equal to R minimum, that is equal to A1 minus A2. If A1 equal to A2 equal to A node, then R equal to R minimum equal to 0. And dear student, what about the I? The resultant intensity equal to I1 plus I2 minus 2 under root I1 I2. So what you are observing here? Resultant intensity is lesser than individual wave intensity. Okay, so brightness here decreases. If I1 equal to I2 equal to I node, then I equal to I minimum equal to 0. Okay, What about the average intensity? What about the average intensity? Dear student, average intensity is I maximum plus I minimum divided by 2. That is equal to I1 plus I2. Why? Because I maximum is I1 plus I2 plus 2 under root I1 I2, and I minimum is I1 plus I2 minus 2 under root I1 I2. So I average is I1 plus I2. So what you are observing here? In case of interference of light, energy is neither created nor gets destroyed. Only redistribution of energy takes place. Only redistribution of energy takes place. Energy gets transferred from destructive interference points to constructive interference points. Okay. So here, this is a case of energy conservation. This is a case of energy conservation. So dear student, in the next lecture, we will see important points about the Young's double slit experiment. Thank you very much.